Ladies and gentlemen, welcome to video number 15 in a series of video lectures which are companions to the book The Fivefold Sun, which was filed at the Bibliothèque Nationale de France in Paris in late 2017. We are today November 21st in the year 2018, about a year later. In video 15, we will introduce the relation between fivefold symmetry in the numerical kinematic of the Sun, its solar cycle, and in its three-dimensional geometry. We will do this through the number 144, which will serve as a go-between between these two spatial and time notions of fivefold symmetry. In part 2, we are back into section 2.8 and 2.9, which deal mostly with the latitudinal evidence, but this is where we will find the 144 rotations seen from a spatial point of view, which will allow us to propose a relationship between the time expression and the spatial expression of fivefold symmetry in the Sun. We today want to reflect on this relation between the numerical kinematic of the solar cycle, which was found in part 1 of the Fivefold Sun as a book, to be based on Fibonacci numbers and generalized Fibonacci numbers, in which the Fibonacci number 144 played a key role because it is the total number of rigid rotations over a quasi-decadal solar cycle, and the fivefold symmetry in the 3D geometry of the solar ball. How can we arrive at pinpointing this relationship? We can try to do this at a specific singular point or latitude point in a cross-section of a rotation profile of the Sun, latitude across the sphere of the Sun, at which the rigid rotation inside the solar radiative zone is also verified throughout the convective zone outward to the solar surface. From a meta-analysis of the literature, it was found in the Fivefold Sun as a book that this angular velocity, which corresponds to the rigid rotation of the solar ball, is verified at the surface near 38 degrees. If we want to be as precise as 4 significant digits, we would estimate that this latitude is 38.25 degrees, but we have an error bar anyway of about 1 degree. We arrived at this estimate in this work almost only from surface measurements. Of course, they supersede interior measurements when you want to have a surface velocity, and that's what we want. And the helioseismological measurements for the interior are difficult to interpret in this case. You see here an excerpt from the book, this table from part 2, which is one of the pieces of evidence that were collected from the meta-analysis, in which you see from 9 estimates, of which 2 can be in fact summed up, we have a mean of 8 estimates that averages out at 38.03 degrees of latitude, where the surface rotation is about 430 nanohertz, which is the rigid rotation inside the radiative zone of the Sun. We, on the other hand, will see now that there is a rigid rotation corridor throughout the convective zone at a certain inclination versus the solar equator, as is found from helioseismological observations, which ends at the surface near this latitude of 38 degrees, and which is supported by a special angle which we find in the proposed icosahedral geometry of the solar ball, the 37.37 degree icosahedral angle. 37.37 degrees is the icosahedral angle for which the angular velocity in the rigid rotation of the Sun, corresponding to 144 rigid rotations across the length of the solar cycle, is verified. We can see this in more detail in this sketch. It is again the 2D projection in perspective of the proposed 3D arrangement with 12 balls, in which you will recognize at this angle versus the equator the 58-degree line, which we call a dividing line in latitude. These would be containing the polar caps into a cone like this. You recognize this line, and parallel to it you recognize a line which is inclined by the same angle and which goes from the south effective magnetic pole, which we equate with the center of this south polar ball, and goes through the center of this ball in the opposite hemisphere. The prolongation of this line from this one through this this outer ball cuts the surface of this outer ball on a line that corresponds to, this is this red line, that corresponds to an inclination of 37.37 degrees versus the equator. This is because we have here a dash dotted line, which is shows the inclination of the center of this ball versus the equator, which is 26.56 degrees. So if you go through the trigonometry of this inclination for this line going across through the center of this ball, and an inclination of 58 degrees compared to parallel to the equator here, you arrive at this intersect here on the surface of this ball of exactly 37.37 degrees. Please note that there is a second intersect which is on this sketch, on this cartoon, which is on the prolongation of the inclination at 58 degrees, which we call a corridor of rigid rotations in the actual Sun. And this prolongation intersects the surface of the circumscribing sphere, i.e. in the case of the Sun, the photosphere, at a somewhat higher latitude, and it is 38.13 degrees if you go through the trigonometry. So in both cases, 37.37 degrees and 38.13, we approach rather closely the estimate that we found for the latitude at which the rigid rotation with 144 rigid rotations through the solar cycle is verified. What you see in the thick lines, which are colored in orange here, is a golden rectangle which is defined by the four centers of outer balls, the two polar ones, and the two antipodal ones here. It is a golden rectangle in as much as its length is 1.618 times its width. So icosahedral geometry seems to determine the inclination of the rigid rotation corridor and the latitude at which it arrives at the solar surface. We had a number of angles to check to validate the presence of icosahedral symmetry in the Sun. And among these angles, they were all checked so far except this 37.37 angle. It is now checked. This angle corresponds to an angle between the center of a face of the icosahedron and its vertex, any of its the face vertices. The 31.7 degree angle corresponds to mid-edge angle to next vertex angle. The 58.28 angle corresponds to mid-edge to opposite vertex angle. And the 20.90 angle corresponds to center of face to mid-edge angle. So we have now checked all of the 6 + 1 major icosahedral angles that we determined before we started going into the evidence. And of course, the last angle, 90 degree, is straightforward. That is how far we can go into our investigation of the interplay or interrelation between numerical, kinematic, and spatial geometry of the Sun for now. And this is the end of video 15. Ladies and gentlemen, I thank you for your attention.